Okay guys, it is time for the ideal gas equation. So those of you who are studying chemistry are going to have a real advantage here. There are some slight differences to what you will have done in chemistry, so do pay attention. So the ideal gas equation. So you need to know where this comes from. Last lesson we talked about how we can figure out the relationships between pressure, volume and temperature for a gas of a constant mass. And if we combine all those relationships, we find that PV over T is going to equal a constant. And that constant is going to in some way represent how much of your gas there is. And that constant is in fact N times R. And please note it is a lowercase n. That's important because a capital N means something different. Now if I just plug that in and rearrange it ever so slightly, that gives me PV equals nRT. Now I know if you plug that into YouTube you'll be able to find some very interesting songs all about it, so you can go and look that up if you really fancy. For our purposes you do however need to know that the lowercase n is the number of moles in the gas. We've talked about the number of moles before, so that shouldn't be too terrifying. And R is just a constant. It's something called the molar gas constant, and its value is 8.31 joules per Kelvin per mole. So obviously our temperatures are going to have to be in Kelvin because the molar gas constant, its unit is Kelvin in there, so it's got to be in Kelvin for everything to work out. So that will be the form that chemists will recognise. However, we are going to at times use a different version. And that requires us to just have a little bit of a play with this equation. So we're going to find something called the Boltzmann constant. Now you won't need to show where this comes from, but I just want to explain it to you so you've got it. So if your eyes start glazing over with all the algebra, don't worry too much. So we're going to go back to what we talked about with the Avogadro's constant. So I have the number of molecules as being my capital N, which is why I said the capitalization matters. So the number of molecules is equal to the number of moles times Avogadro's number. If I just rearrange that, that gives me that the number of moles equals the number of molecules divided by Avogadro's number. Shouldn't be anything too horrific yet. We know that the ideal gas equation is PV equals nRT. I'm now just going to plug in this rearrangement into this equation, which will give me that PV equals the number of molecules divided by Avogadro's number times RT. Then I'm just going to rearrange that slightly. So all I've done is I've shifted the R to the top of the fraction here and the N, just pulled it out of the fraction. Now it all means exactly the same thing, but I've done that because I now have R divided by Avogadro's number. Now R was the molar gas constant, so a constant, and Avogadro's number is the number of molecules in a mole, which is also a constant. So I have a constant divided by a constant. So if I do that, that's going to be a new constant. And that constant is in fact what we call the Boltzmann constant, which is a K. So if I now plug that Boltzmann constant in, which by the way is 1.38 times 10 to the minus 23 joules per Kelvin, if I plug that in, it gives me a new version of the ideal gas equation where I have PV equals the number of molecules times the Boltzmann constant times the temperature. So now I have a version of the ideal gas constant that I can use when I know the number of molecules. The other form, this one up here, PV equals nRT, I can use when I know the number of moles. So I have two options and I can use whichever is appropriate based on the information that I have been given. That's why it's useful to have both of them as a tool. So we will practice using these and doing all sorts of calculations with moles as we go along. Next thing we need to talk about is coming back to energy and temperature again. So we've talked about the energy and the temperature of gases quite a lot so far. But now that we have the Boltzmann constant, we have another way of looking at how much kinetic energy our gas molecules have. And the equation that we're going to use is that the kinetic energy is equal to 3 over 2 times the Boltzmann constant times the temperature of the molecules. So that is my average kinetic energy of my molecules. And obviously we already know that kinetic energy is a half mv squared. Now the V is the average velocity of the molecules. It's not going to give you each individual one, and they're not all going to be the same. There will be a range of speeds, but this gives us a way to calculate the average speed. So, as I said, they're not all the same speed. In fact, they're going to have a continuous distribution. If I plot a graph of the speed of the molecules against the number of them that have that speed, we get a lovely bell-shaped curve. This is called the Boltzmann distribution. So it just shows you how the speeds of the molecules vary. And real important note, if we say that the average is here, I will always have some molecules that have more than the average and some molecules that have less than the average. Now, that is glaringly obvious. I know that, and I know that you know that. I also know that if in an exam you're asked how could something possibly happen if the average temperature isn't high enough for it to happen, you all seem to forget that if the average temperature is it's X, then some of the molecules have more than X, so some molecules will have enough energy for whatever it is to happen. So just please remember that we are talking about average energies here. So there is just a line of our Boltzmann distribution. Sorry, my brain switched off for a second there. So this just gives you the average, regardless of the interactions that happen. Obviously, some are going to get faster, some are going to get slower, they're going to interact with each other, but this just gives you the average distribution. Now, something you can be asked to consider is how would changing the temperature change this distribution? So what we've got now are two graphs showing a distribution of two different gases. One that is at a lower temperature and one that is at a higher temperature. Now, for our higher temperature one, we can tell it's at a higher temperature because the peak happens at a higher speed than the lower temperature. Really, really obvious. But the other thing to pull out is the fact that our higher temperature graph is flatter. So the temperatures are more dispersed. They are not as uniform as they are in the low temperature one. I've got a much narrower peak for my low temperature. Once we get to a higher temperature, they begin to spread out. The difference between these, the energies of the molecules gets bigger. But we do end up with a higher peak, but flatter. Okay, so I've said a couple times that we're looking at the average speed. So when we do E equals 3 over 2 kT, that gives me the average kinetic energy, which gives me an average molecular speed. Now, it's not the average you're used to. It's an average called the RMS, so the root mean square of the speed. So basically, it's really straightforward. If a gas has n molecules and they each have the following speeds, the root mean square speed is given by the sum of the square of the speeds divided by the number of the molecules and then square rooted. It just gives you a way to get rid of the fact that these could be velocities, so some could be forwards or backwards. You often find this with, if we're looking at the average voltage with an alternating current, then we would use this because it smooths out the positives and the negatives because we've squared, so that gets rid of that. It just evens it out a little bit more. So this is what we use for this. It's called the root mean square. I doubt they're going to ask you any questions specifically on this, but it is explicitly on the specification this year, so I just want to make sure that you have got it really clearly. So just to give you an example, my advice is just pause for a second and see if you can do it, then I'm going to show you the answer. But the question is to find the RMS speed of 4 molecules that have the following range of speeds. So if you're going to pause, now's your last chance. Okay, so first thing you want to do is square those 3 speeds, which would give you the following. Then add them up and divide by 4, because there's 4 speeds. And I then take the root of that average of the squares, and that gives me the RMS speed of 344 meters per second. Okay, so we've covered a fair bit of theory in here. Just make sure you're really, really careful with your n's. So are you talking about moles or number of molecules? And if so, which of the constants do you need in your ideal gas equation? We'll have a bit more of a look at some of these graphs. I have a nagging suspicion this could be the kind of thing they could ask you a slightly more extended question about, because there's a lot that you can say from those graphs and being able to think about what's going on. And it also links in quite nicely to some of the mechanics and the energy stuff from AS, because we are looking at half mv squared, which is one of our AS equations. Okay, so I think that's about it for this video. So remember, if you do have any questions, just remember to ask me, and I will see you in class.